I am Steve Cohen. I am, stay near the mic, Chief Operating Officer and a co-founder of Basis Technology. And as you see from the title here, I'm here to talk about the front lines of finance. What does that mean? What we're talking about here is how Basis Technology has applied what we've learned and experienced over the last 2 decades in applying NLP to solve problems for national security to the problems of finance or financial crime in particular. So I want to start off by telling a story. Is anyone in the room familiar with what's called the, no, I'm blanking on it, the liquid bomber case from 2006? Okay, a couple of people, surprisingly few to be honest. So in 2006, in August of 2006, 7 airplanes didn't crash into the ocean. 7 airplanes did not get bombs exploded on them, causing them to crash. And yet there had been a plot to do just that. These 7 airplanes, you can see you can see on the map, were chosen and carefully selected by a group in the UK who was going to have people board these with bombs made from drink containers where they were going to replace the contents with explosive material and explode them while they were over the Atlantic Ocean. That didn't happen. It didn't happen for a wide variety of reasons, but among those reasons, strategic among those reasons, was the ability of the intelligence communities in the UK and in the US to analyze data that they had found once they suspected the plot, and they analyzed this data using natural language processing tools to discover some of the links between the players and the information that they received. So I like to start off with this story because this is an actual, tangible, real instance where NLP saved lives, right? And that, as much as we like to make money, and I'll bet a lot of people in this room like to make money selling NLP-based tools, in a way it feels even better when you can say you saved lives with it. Let's talk now about finance and financial crime. This is a small selection of headlines that one of our bank partners handed to us, showing some of the financial fines that have been handed to financial institutions due to their failure to comply with financial regulations. You can see that this is a bunch. There are literally, over the last a decade and a half or so, many dozens of these. It's still a problem, not surprisingly. Last year, $10 billion in fines. $10 billion. So I mentioned the term financial institution. Well, what is a financial institution? Well, we think of banks and maybe your finance company, and in the US we have the likes of Fidelity and Schwab. Does anyone think of Apple as a finance institution? But Apple is subject to financial regulations, and last year was fined by the US Financial Crime Enforcement Network, or FinCEN, substantially for failure to comply with counterterrorist financing laws. So Apple is effectively a financial institution. And if Apple is a financial institution, virtually at least every larger company is. Here's a short list of some of the companies that have been fined. These are the funds that were fined last year. If you can see the names over on the left, a lot of them don't sound like banks. Stanley Black & Decker, for instance, makes tools. So the point is, this applies to a lot of companies. It's not just the Morgan Stanleys of the world. So I'm talking now about what is the problem that the banks face, or the financial institutions, or every company face, having to do with financial crime enforcement. What does it have to do with that first story I just told? We believe it's really the same set of problems that they face. The problem is basically, how do you find the bad actors given your signals? In our case, we care about the text signals. That's in the liquid bomber case, the text signals were one of the major sources of discovery that they used. So what does it mean to find a bad actor from text signals? Here is a canonical comic of a bad actor. This is, or in the industry, we just call them bad guys. All right, so here's your canonical bad guy. How are you going to find him? Are there any data scientists in the room? A few. So if you're a data scientist, what's the first thing you do? You build a model of a bad guy. Here's a model of a bad guy. Right? You can tell. He's got the mustache. Must be a bad guy. So that's great. Here's a model of a bad guy. How do we use it to catch other bad guys? This model doesn't help us. So instead of just talking about building a model of a bad guy, we have to think about what is it? What constitutes bad guyness? I've got two answers for that. There's two types of models that we know how to build. On the left is an illustration of simply finding whether the person you're talking with, the person, for instance, who's trying to establish a bank account, is already known to be a bad guy. As in, published on one of the lists, the U.S. has the OFAC, the Office of Foreign Asset Control. Every country has a list. There's companies that will sell them to you. The illustration on the right is you can also determine badness by looking at their behavior. So these are the two ways I know to distinguish bad guys from good guys. So if you want to, let's talk about whether we could build a model against either of these. The first one, I said there's lists. This is an example of the US OFAC list, or a short segment from the US OFAC list, that contains information about known bad guys, known terrorists. It's a lot of, in general, it's terrorists on this list. So that's one type of data we can build a model from. This is, if you're a bank or a financial institution, and you've discovered a potential bad behavior, you have to file a report called a SAR in short with FinCEN in the US. This is a small segment. I'm not going to read it to you, but basically it is describing how they researched and found a set of behaviors, moving money around in suspicious ways. So this is something that you could use to build a model of bad behavior. I'm going to focus on the first one. But first, I want to talk about the intelligence cycle. Is anyone in the room familiar with the intelligence cycle? This is a standard practice in the intelligence community for how you manage discovery and usage of intelligence information. This is very much standard across most intelligence communities. You can read the whole thing. I want to focus in, however, on these three parts: collection, processing / exploitation, and analysis. I focus on these because these are the areas where natural language processing can be useful, and I'm going to relabel them for a second. The first one is acquiring the list. That's actually relatively straightforward, except when it isn't, but using the OFAC list as an example, it's very easy. Anybody can download it. The second is where the fun really happens, connecting the dots. How do you know that the behavior or the person who you're trying to match up to a list is the one you care about? This is where the NLP or other techniques come into play. And then finally, the decision process. That actually generally still is, and I think should be, handed off to a person to look at the collected data so they make that decision. So I want to focus on this connecting the dots some more. And connecting the dots in this case, I'm going to talk for a while about how do you match someone whose information you've gotten against one of these lists. This is an example of one entry from this OFAC list. You can look at the fields that they have available here. There's not a lot of them, and they're not particularly reliable. Right? If you want to look at the person's birth date, well, they were born sometime between 1972 and 1974. That's not particularly reliable. You know they're from New Zealand. The one major thing, the single most important, or what I would refer to as a primary key in database speak here, is the person's name. That's the starting point. You want to use all the information you can, but across the entire OFAC list, the one thing that's consistent is you have a name. Sometimes you have a bunch of names. There may be aliases showing up, but you do have names. So that's great. You can simply take the name that you've got of your potential customer and compare it against everyone on the OFAC list. Sounds easy. Well, not so much. Names are actually really tricky. This is just talking about names as they appear in English. There's a lot more that goes on in other languages, but we've got 14 different ways that names can vary represented up here. This is our standard list of ways that we think about name variation. 14 different ways that names can vary. So if you want to do this name matching, you just want to be able to tell whether this name that you got for your prospective customer and the name on the list are the same, then you want to pay attention to these 14 different ways they can vary. Well, great. So you're going to build a model again. People have been worrying about this problem for about 100 years and have developed some approaches. Two of them are represented here in a very short way. One's called SoundX, the other is Metaphone. As you might be able to tell from the names, they both are looking at phonetic behavior of the names. And I won't dive into it, but these don't work very well for most names nowadays. They worked really well when the Bell system, Bell Telephone invented SoundX in the early part of the 20th century for the limited use case. These techniques will not handle those 14 types of problems that I showed on the previous slide. So that's great. It's 2020. We'll just find our friendliest Sesame Street character and build some sort of neural net that'll match names. This doesn't work either. Not directly. It doesn't work because those neural nets are designed to look at contextual clues, to match up contextual clues. If you just have two names, you don't have a whole lot of context. It's not that simple. You cannot simply take a bunch of names that you think sound alike or are the same name and dump them into a neural net. Here's a reminder of what those problems look like again. So what do? Let's break the problem down. Let's take a look at these 14 different ways that we know of that names vary and think about them one by one. On the right, I've got an example of a query, an example of a match that you're trying to make. So the first thing you might do is build a model for the phonetic similarity between two names and get some score from that. And then, just to use two examples, then you could take a look at nicknames and build a model for that. Full disclosure, the model for nicknames is pretty much always just a list because there's no easy programmatic way that I know of to go from Dick to Richard. But I'm going to treat that list as a different form of a model. You do that across all of these 14 different ways that names vary. I didn't put a plus sign in there, but you basically add up the results or you do a linear combination or whatever combination you want of the results, and you can get a match that takes into account all those different types of variation. Any one of those models could in fact be a neural net. There's places you can still use BERT if you really want to. And practically speaking, it's probably kind of slow, but neural nets would fit in here. So you get a result. And this result is taken from one of our customers' actual products, a company called Vital4Data. And the input into their system is the name. You see it up at the top. And then you get a list back out. So that's great. We've solved this problem, right? How many times have I said 14? Quite a few. There's a lot of models. What do you think is the remaining problem you have to deal with? You're going to run all those models on every pair of names. Guess what? It's going to take forever. It's way too slow. So you got one last step you got to do. And the final step is you take off the data science hat, you stop thinking about the models, and you start thinking about performance tuning. Or if you're actually a programmer, you'd call it hacking, right? You find some way to just make this work a lot faster. Ultimately, you treat it like a search problem. And search engines start by having a recall phase where they get as many relatively close candidates as possible, and then winnow that down with sorry, blanking on the words here. But winnow that down to the list that you need. And this works here too. You start with what we refer to as a high recall key. You get the list of everything that's within some reasonably large, actually, epsilon of the answer across the variety of different behaviors you care about across those 14. And then you run your comparatively slower 14 different models across all of those in finite time and get a result that's very performant. That's actually my last slide, but I'm going to finish with one data point, which is we built this. We built a product called, we refer to as the Rosette Name Indexer. And every single day, our customers do 150 million name matches using this. High reliability. That's, those name matches are being done both for financial compliance and for national security. So that's across both of those types of use cases. So I'm going to, as the end of my slides, I probably have some time left. Let's see. So are there any questions? Yes?
Could you say some more about the data you feed into these models?
It varies a lot. It really depends upon each one. So I'll take, for example, the phonetic models, because in some ways they're the most interesting. The phonetic models look at known phonetic behavior between languages. I left out so many details, but one of the things we put in is a knowledge of the phonetic behavior of characters within a language. That's relevant if you think about the fact that, say, French, the same letters in French have a different phonetic behavior than they do in English. We take that into account. So you have that. And when we were first building it, we ran a bunch of what the team referred to as parrot sessions, where we literally had people looking at the pronunciation. So we had not a crowdsource, but we have an annotation, a phonetic annotation, by showing people the names and finding out how they pronounce them. That's how we constructed it. I'm not quite describing what it looks like, but that gives you a rough idea. Is that sort of what you're looking for?
All the names, variations of names. You can't possibly get all the richness of variation just from some wanted lists, what you mentioned at the beginning.
There are surprising, yes, you're exactly right. The OFAC data, the wanted, the bad guy lists, those number in the thousands or maybe tens of thousands. There are data sources that provide much larger sets of names. So in the US, we have what's called the Social Security Death Master Database, which supposedly, through certain dates, contains the name of everyone who's died. It's pretty morbid, and then they started collecting that a long time ago. So you actually have a lot of variety of names as they've appeared in the US, and we've accumulated data like that across a whole bunch of other regions as well. Was there a question there? Sure. Yeah, so for the full-on system, we're focusing at our company on the NLP and the name matching, but you're exactly right. The actual deployed systems that our customers build, and we're starting to work more in this space, do a full record match, a record link, and look at the rest of the data. And again, have some linear combination between the fields in the record. if it's available. That example I showed is an actual example from the OFAC list. And so if you tried to take date of birth there, you could do it. It said he was born sometime between 1972 and 1974, right? So you can certainly use that, but it's obviously, as I said, not particularly reliable. That's right. Again, you get some value from it. So you use all the information you can. Is there another question? Okay. Well, thank you all very much.